When the H-21 landed on the unprepared site, a small cloud of dust developed. There were no visible signs of erosion on the site. As the XV-5A started a descent above the unprepared site, a light dust started blowing. At 60 feet, the intensity of the dust built up. It appeared to be most intense when the aircraft was about 30 feet high. At this time, some chipping of crusted dirt could be seen. It can be noted that dry dirt in the tire tracks tends to chip off first. As the aircraft lowered to 2 feet, much more chipping of the surface dirt was recorded by the wing camera. Just before touchdown, the dust cloud appeared to diminish. The pilot reported that chunks of dirt were thrown outward and none hit the aircraft. The RPM was reduced to 90%, while the XV-5A remained on the ground. Liftoff produced less cloud than landing. Site inspection revealed that a portion of the ground under the fans was eroded about 2 inches down to a moist clay-type soil. In the aerial view, a swept area with a radius of some 40 feet from landing point was noticed. Inside the circle, the ground was free of loose dirt and pebbles. The silty sand at this site, which had been prepared as a parachute drop zone, was loose to a depth of 18 inches. It provided an almost inexhaustible supply of loose material. As the H-21 descended, a silt cloud began to form at 50 feet. As the helicopter continued down, the cloud grew in intensity until at 1 foot, the H-21 was partially obscured. This was the first test in which the aircraft was hovered tail to the wind. The wind was 7 knots. In this aerial view, note how the cloud formed is blowing around the XV-5A, forming a trough. On previous tests, the XV-5A operated with the nose into winds from 0 to 3 knots. It was noted that any dust clouds formed were in front of and close to the nose of the aircraft. Observation of this phenomena, together with the experience gained from low-speed passes earlier in the program, led to the conclusion that conditions would be more favorable if the XV-5A were operated tail to the wind. The similarity between the effect created in this test and the effect evident in the water test should be noted. At the lowest point in the descent, estimated to be below 10 feet, the XV-5A was obscured. No landing was planned on this surface. However, the pilot felt a landing could have been made if necessary. In these views of the same descent, taken from another camera angle, the dust cloud started coming over the wings at 40 feet. This cockpit camera shows the trough effect. The pilot reported that as the aircraft descended, the clouds converged in front of the aircraft and that he lost visual contact with the horizon. He reported that visual contact with the ground was maintained. Inspection of the area after the test revealed that portions of the top dry, powdery surface had been blown away. However, the sparse vegetation remained. This site, the last in the soil erosion test series, presented the greatest hazard to the aircraft and propulsion system. It consisted of loose gravel, averaging 1/4 of an inch in depth over dry hardpan. The vertical descent of the H-21 produced very little ground disturbance. A small amount of dust was created, but the terrain was not affected. During the descent over the gravel, a light dust started rising when the XV-5A approached 50 feet. In this view from the wing camera, the sweeping action observed on all soil erosion tests was particularly evident. The gravel can be seen moving outward in a radial pattern. At 25 feet, the XV-5A created a large, dense dust cloud. The pilot could see the gravel being swept outward from the aircraft and some dirt clods chipping from the surface. Note that all gravel has been swept from the area. Despite the apparent density of the dust cloud, this cockpit camera shows the pilot's view of the horizon. As the pilot lowered the aircraft to 1 foot above the ground, then landed, he could see the dirt chips still blowing away from the aircraft. As in previous tests, immediately prior to touchdown, the intensity of the dust was reduced. On takeoff, very little dust was raised. Cockpit visibility was good, and the XV-5A was not obscured. Inspection of the gravel and hardpan area after the flight revealed an area 50 feet in diameter, completely swept of all gravel and loose rock. Some erosion of the hardpan surface was evident. Following the complete erosion test series, the J-85 engines and the lift fans were removed from the aircraft, disassembled, and thoroughly inspected. No foreign object damage was found, nor was any deterioration detected in the engines, ducts, or fans. The purpose of this test was to determine the effects of pressure, temperature, and stability on an instrumented dummy. This was, for all practical purposes, a test simulating a potential rescue mission. 50 feet of cable and a helicopter hoist were used in the test. As the XV-5A made a vertical takeoff and assumed a hover position over the runway, the dummy was lifted clear of the ground, oscillated slightly, then stabilized under the aircraft. Instrumentation for these tests consisted of an oscillograph in the dummy chest cavity to measure cable loads, tempolac on the helmet and shoulders to measure temperature, a wing-mounted camera on the XV-5A, and ground cameras. The pilot operating the electrically controlled winch raised the dummy closer to the aircraft in increments of 10 feet until the head was within 2 feet of the main landing gear wheels. Except for a slight rotation, the dummy was stable over the entire range of the lifting operation. It might be observed that as the dummy gets closer to the aircraft, the turbulence diminishes. The dummy's static weight was 235 pounds. The peak cable load recorded during the lifting operation was 330 pounds. For this test, a mirror was installed to give the pilot constant surveillance of the dummy and cable under the aircraft. The dummy was lowered and again experienced no stability problems. After the dummy was lowered, the aircraft translated forward at 30 knots. No problems were experienced with the dummy. During this translation, the cable loads remained constant at 260 pounds. The tempolac shoulder patches covered a temperature range from 150 to 600 degrees Fahrenheit. None of these were discolored, indicating that temperatures were less than 150 degrees Fahrenheit. Tempolac on the helmet covered the same temperature range. Also installed on the helmet were pyrodyne templates covering a range from 200 to 350 degrees Fahrenheit. There was no discoloration, indicating that temperatures on the helmet were also less than 150 degrees Fahrenheit. Following analysis of the dummy tests, with special emphasis on safety, the human element was added to the simulated rescue mission test. The purpose of the test was to evaluate a man's ability to reach a rescue seat or a sling. The subject was dressed in flight clothing, including gloves and helmet. The first test altitude was 60 feet. The subject walked to a position directly under the aircraft and moved around freely. The second test altitude was 40 feet. The subject, with some effort, was able to reach a position directly under the nose wheel, where he raised his arms to indicate his ability to reach a rescue sling. The third test altitude was 25 feet. The subject was able to walk to a spot within 5 feet of the rescue point. The surface wind was estimated to be in excess of 60 knots, which prevented further penetration into the area. In the fourth test, the wheel height was 10 feet. The subject approached to within 15 feet of the rescue point. The surface wind was estimated to be in excess of 70 knots, which prevented going further. The temperature environment under the aircraft created no problems for a human rescue, and pressures at 40 feet permitted maneuvering to a rescue position. The broad spectrum of VTOL flight capability inherent in the U.S. Army XV-5A lift fan aircraft was shown in the previous erosion tests. Now, in a simulated mission profile, Val Schaefer, Ryan's chief engineering test pilot, who flew the XV-5A in all the erosion tests, and Major William Welter, the Army chief project pilot, will demonstrate the capabilities of the aircraft. After a brief inspection, Schaefer in the XV-5A and Major Welter in the Army UH-1 helicopter will air taxi from the Army Test Activity Hangar to a mission over the Mojave Desert. The XV-5A lifts off vertically with the helicopter, air taxis it out to the Edwards Air Force Base Lake Bed, and departs for a simulated Army campsite located at the Naval Ordnance Test Station, China Lake, California. Flying on fan power at 85 knots, the XV-5A converts to conventional jet flight. The nose comes up, the fan doors close, and the XV-5A is a high-performance jet aircraft. Approaching China Lake, Schaefer reconverts the aircraft back to fan flight, then begins his descent and approach to the campsite. At the Army encampment, two command tents, a smaller tent, a U.S. Navy CH-34 helicopter, Army enlisted men, and typical aircraft resupply equipment, plus several standard Army vehicles, were stationed in the immediate area. After a low approach to the landing site, the tail camera records the dramatic landing of the XV-5A about 60 feet from the closest tent. Following a high-performance climb-out, the XV-5A converts to jets and heads back for Edwards. At Edwards, the XV-5A makes a fan-powered descent at the rate of 2,500 feet per minute. Taxis over the runway, turns into the wind, and makes a vertical landing. In the Army Flight Test Program, the XV-5A has demonstrated a versatile capability. The program, managed by the Army Aviation Material Laboratories, will continue through 1966 at Edwards, as the XV-5A research aircraft probes deeper into the challenging jet VTOL environment.